Hello everyone, this is Giuseppe. I hope everyone is healthy and doing fine. Uh, I want to start this video by thanking the organizers of this conference for the opportunity to speak. And let's dive right in. Today I want to talk about sequences of Itchin representations of tree type. So let me start with an introduction. So uh, our classical motivation for this talk comes from tech-linear space. So tech-linear space is a very important object in low-dimensional topology. One starts by fixing a surface of genus bigger than 1, and the tech-linear space is the space of hyperbolic structures on S. And one can think of this in a more algebraic way by identifying it with a subset of a character variety, so group homomorphisms from the fundamental group of S into PSL2R up to conjugation. And it turns out that these representations are discrete and faithful, and the tech-linear space is a vector space of dimension 6g minus 6, so only depending on the topology of the surface. And studying three-manifold and trying to understand the topology of three manifolds better, Thurston introduced a compactification of the tech-linear space, where he attached the geometrically meaningful boundary to the circular space so that the resulting space is a closed ball of dimension 6g minus 6. The boundary points of this Thurston compactification have then been reinterpreted in many different ways. So one way we're going to focus on is the point of view of Besvin, Amberg, Schell, and Polan, where when we take a sequence of representations in tech-linear space, we see that the hyperbolic length functions of this sequence converge to the length function of a pi1 action on a tree, on a metric tree. So today we're going to try to think of a more general setting. So I want to focus first for like the first half of the talk on the space of convex RP2 structures. So the space of convex RP2 structures is essentially a generalization of tech-linear space, and we're going to see why. But a convex RP2 structure is a bounded strictly convex set containing a affine chart in RP2, together with an action of pi1 of S via projective isometries, so that the quotient omega times the image of pi1 of S is the surface. And we can identify the space of convex real projective structure with a subset of a bigger character variety. So now instead of PSL2R, we're using PSL3R, which is the space of projective transformation. And again, this is a proper generalization of tech-linear space, because if we look at the Klein-Beltrami model of H2, the tech-linear space sits naturally inside the space of convex RP2 structures, but the space of convex RP2 structure is larger. So this, for instance, Goldman proved that this space is a vector space of dimension 16g minus 16. So again, we have this space, we have tech-linear space inside of it. So a natural question is, well, if I go to infinity in the space of convex or projective structures, when does my limit look like a point in the boundary of tech-linear space? So before we can formalize this question, we need to introduce a generalized length, and that's the Hilbert length. So the Hilbert length can be defined in at least a couple of ways. So one way to think about it is take a closed curve on the surface, find an axis for the corresponding to group element in the universal cover omega. Then this axis determines one can take 4 points along this axis as in the picture. And then when we have 4 points on a projective line, we can take a cross ratio, and this is going to end up being the Hilbert length of this group element, or this conjugacy class. Or another way, which is more algebraic, is that a group element defines a matrix, and we can take the eigenvalues. Turns out that these eigenvalues are distinct. So the Hilbert length is going to be the logarithm of the ratio between the highest eigenvalue divided by the smallest eigenvalue of this matrix. And so maybe to rephrase, the main task is the goal of this talk is to try to find explicit non-trivial conditions for a sequence of convex projective structures so that the limiting object is a pi1 action on a tree, but this time with respect to the Hilbert length. Okay, so we want this explicit description of certain boundary points for the space of convex projective structures, and we're going to make this explicit using some parameterizations that we're now going to briefly recall. So let's start from the Teichmüller case. So for Teichmüller space, this parameterization is what's the classical shearing parameterization of the Teichmüller space. So one starts by fixing a pair of pens decomposition of the surface, and then on each pair of pens, one chooses an ideal triangulation. So essentially, we cut the pair of pens into two ideal triangles by using some open leaves that wrap around the boundary curves. So when we lift it to the universal cover, and here I'm choosing the Coimberg-Tramier model of the hyperbolic plane, we get that these open leaves lift to straight lines. And for each of these open leaves, we get a quadrilateral in the hyperbolic space, an ideal quadrilateral in hyperbolic space. So we can take the cross ratio of these four vertices and given an orientation. What we can do is we can take our open edge, let's say open leaf E, which is the middle one here, and we can use the PSL2 action on the hyperbolic space to send the vertices of E to 0 and infinity, then the remaining vertex of the triangle on the left to -1, and then the remaining vertex on the triangle on the right is going to be some positive number. Let's call it SC, and then we can take the logarithm of this number, and this is going to be the shear parameter of the open leaf E. When we are next to a closed leaf, it's going to be a little bit more tricky. We need to choose a little bit of more topological data. We need to choose an arc which is transverse to this open leaf. And when we lift it to the universal cover, this open arc is going to single out for us two triangles, one to the left and one to the right of an axis of this closed leaf. And then once we have chosen these two triangles, we have 4 points in the boundary of each two, and we know how to give a real number associated to this, which is the cross ratio of these 4 points. And so this is going to be the shear along this closed leaf. Thurston proved that these parameters combine to give a parameterization of Teichmüller space. We have a little bit too many parameters. We have 9g minus 9, 3 on each pair of pens, and then 1 for each closed leaf. But there are gluing conditions. So if you have two open leaves that's parallel on the same side of a closed curve on the pens decomposition, then the length of the closed curve is the sum of the shearing of these two open leaves. When we try to do the same construction in the context of convex projective structures, new parameters arise. So we fix the same topological data and we lift it for convenience to this properly convex set inside a fine patch of RP2. And general theory tells us that this convex set has a C1 boundary, so there is a notion of tangent lines. So when we take one of these ideal triangles, each of these vertices of this ideal triangle has a tangent line next to it, and we can use the SL3 action to normalize two tangent lines and 3 of the points as in the figure in the slide. But then this vertex 1 minus 1, 1 has a tangent line. This tangent line, there is a whole one family possibility of tangent lines passing through this point that we don't know. So we need to associate a parameter to this, and one can do that in the way it's described in this picture, and we get a positive parameter, which is the triangle parameter, and one keeps track of the logarithm of this triangle parameter. Then, once we fix parameters for the ideal triangles, the rest of the construction is very similar. So when we have an open leaf, we have two adjacent ideal triangles we can normalize our picture, and then we need to give parameters associated to how to choose the vertex of the triangle on the right. And turns out there are two parameters here, and so we keep track of the shear parameters along this leaf E as the logarithm of these two positive parameters, and a similar construction is done next to a closed leaf. And so Fock and Gonchar introduced these parameters, and they parameterize a space very similar to CS, but the way I'm describing this parameterization actually is due to Boron and Dreyer. But anyways, these parameters combine to a parameterization of this space of convex projective structures. Again, there are too many parameters, so there are some gluing conditions involved. And these are due to Boron and Dreyer. So if we have two edges and two triangles that spiral on the left of a curve in the Pence decomposition, and we denote the eigenvalues by lambda 1, lambda I, rho C, then the simple root lengths, which are the ratio of two consecutive eigenvalues, are explicit functions in terms of the shear and the triple ratio, the triangle parameters. And they're written in the slide, so the sum of these parameters. All right, we developed the tools to start going to infinity, so let's do that. Okay, let's start with Teichmüller as usual. So we take a sequence of representations into Teichmüller space which leave a very complex set, and let's focus on a pair of pens. So when we focus on a pair of pens, there are two options. Either your length functions or your boundary curves are growing at comparable rates, meaning that every length of every curve is growing at most as the sum of the other two, in which case your pair of pens degenerates to a theta graph, meaning that the upper body length of curves is converging to the length of pi1 action on a theta graph, like depicted, where for instance, the big outside loop is the loop corresponding to one of the three boundary components. Or there is maybe one boundary curve of the pair of pens which is growing faster than the other two, is growing faster than the sum of the other two. And so in this case, your limiting action is an action on a dumbbell. So for instance, C3, which is the curve is growing faster, the length function is described by moving along these segments, this middle segment, and then doing a loop around the dumbbell, then going back on this middle segment, doing a loop around the other dumbbell. These are like weighted graphs with length function attached to each edge, and that's a way to describe it combinatorially. We can do this description not just in terms of length, but we can do it in terms of shearing coordinates. And what's happening is that when we look at the graph, we have that this condition about the length functions of the length function not growing comparable with each other is the same thing as saying that on all the open leaves the shearing coordinates are positive, and the description of the length functions on a dumbbell is the same thing as saying that the shearing coordinates along one of the open leaves is negative. And we can push this even further. We can describe the length on the metric graphs, limiting metric graphs, in terms of the asymptotic behavior of the shearing coordinates. So this is one of the main motivations for this work. So this a very explicit description in terms of the shear coordinates, thus it pushes through the space of convex projective structure. So this description motivates a new definition we make, which is a sequence of three types in the space of convex projective structure. So we saw that for convex projective structure, we have these new parameters, which are these triangle parameters, which in some sense are a main dissimilarity from the case of Teichmüller space. So if we are a sequence of three types, what we want is that these triangle coordinates don't grow as fast as the shearing coordinates. They're not as dominant. And then we want that on each leaf, what's happening, where either all the shearing are growing or all the shearing are decaying. So there is no mixed behavior. And again, the main motivation is from Thurston, but there is also like combinatorial descriptions from a paper from 2019 from a paper I wrote in 2019, my thesis. But worth pointing out that one can also produce non-trivial explicit example just by hand, just using the shear coordinates and describing the coordinates. And so a very easy corollary of our main theorem, which is going to happen later, is that on a pair of pens, if you take a sequence of representations of tree type, as defined above, with respect to the Hilbert length, you converge to either a theta graph or a dumbbell, very explicitly. And then, of course, once you have this degeneration along a pair of pens, you want to glue them together. And so the classical result is that if the pens curve, the boundary of the pens are bounded below by uniform constant, then you can glue these asymptotic pair of pens to each other. And we have a theorem which is very analogous. We need to have a uniform bound for the simple root length, of this boundary curve, and then we have a little bit of a technical conditions regarding the shear coordinates of the closed leaves. All right, so far we focused on tachymeter space, space of convex projective structures, and we saw some early results. But the real point of view is more general. So let's start talking about Hitchin representations and Hitchin component. So tachymeter space and space of convex projective structure are examples of Hitchin components. So these are components of this character variety of the Lie group PSLDR, and turns out that one of the defining properties of these Hitchin components is that they contain an embedded copy of tachymeter space. These were introduced by Hitchin, who proved that these components are all vector spaces of dimension depending on the dimension of the Lie group and on the topology of the surface. And then they were studied extensively by many people, but like very early works were the Labourier, Fock, and Goncharov using different points of view. They both proved that representations in the Hitchin component is discrete and faithful, as if it were, as happens for tachymeter space. And every time I take a curve on a closed curve on the surface, the representations has distinct eigenvalues, so we can define notions of simple root lengths and Hilbert lengths. So these are main examples of what are known as higher tachymeter spaces. One of the key properties of Hitchin components is they come with limit maps. Okay, so these are row equivariant, positive and Frenet. I'm not going to define these names, but they're very nice properties of a map from the boundary of the fundamental group of the surface. The fundamental group of the surface is a word hyperbolic group, so it has a natural notional boundary, into the space of flags in R to the D. And I'm not going to define this, but we have examples. So for d equal to 2, this is a map from the boundary to the group to the boundary of hyperbolic space. And for d equal to 3, it's a map to the boundary of the convex set omega plus the tangent lines at each point on the boundary. Okay, so this forms a flag, a point and a line passing through that point. So these are going to be these are some of the main tools we use in this work. And what happened, like we already seen all of this in dimension 3, but so Fock and Goncharov parameterized the modular space of transverse flags, and they connected this to this theory of the theory of total positivity to loose sticks. And so there are parameters that generalize the triangle parameters and the shear parameters. And then Bonon and Dreyer used this to parameterize the Hitchin representations using these gluing conditions involving simple root lengths. So to be more precise, one fixes the representation of the Hitchin component, fixes the same topological data, so the leaves and the transverse arcs, and then for each open leaf or closed leaf, we have d-1 shear coordinates, and on each triangle we have d-1 choose 2 triangle coordinates, and then on each closed leaf we have d-1 gluing conditions involving the simple root lengths. And so the main task, which is generalization to all dimensions of the main task from the very first slides, is to find non-trivial conditions in terms of the shear and triangle coordinates so that the sequence in the hitching components converges to a power action on a tree in terms of the Hilbert length, which is this ratio of the top by the bottom eigenvalue, and then you take the logarithm. And so the results are, and the definitions are very similar. So the main definition is this new definition of sequence of tree type, where the triangle coordinates don't grow as fast as the shearing coordinates, and on each leaf your shear coordinates either all weakly grow or they all weakly decay. And then the theorem is that on each pair of pens in all dimensions, your sequence of tree types converges to a theta graph or a dumbbell. And we conjecture that for d bigger or equal to 4, one can glue these representations across pair of pens. And there is the second conjecture is a little bit more optimistic, that this is an if and only if statement, so that your sequence converges to a power action on 3 if and only if you're tree type for some pens decomposition. So what is the strategy? So this last slide is about the strategy, how to prove all these things. So this main result, the main technical result, is in terms of the theory of positivities and cluster mutations. So the main achievement of the work is to use an asymptotic description of full control of cluster mutations and combine this with all these gluing conditions we've been keeping track throughout the presentation to kind of understand how these parameters behave when you're going to infinity. And then we use this asymptotic description to produce a limiting graph for a sequence of tree type on a pair of pens. And then another big part of positivity that we use is that we use the description of the matrices associated to closed curves to compute the asymptotics of the Hilbert length along a closed curve. And in dimension 3, we have this extra result where we can glue pair of pens. And so here, the main achievement is to describe triangle coordinates nearby the closed leaf and keeping track of what these triangle coordinates look like, mainly to be able to prove that if I take triangles spiraling towards a closed leaf, the triangle parameters of these triangles stays bounded. So this is the end of the talk. If there are any questions, and we are having an office hours with Ariel and JP on Thursday, and the main reference is the paper. It's on the archive. Thank you.